Welcome to LeetCode Problem 242, Valid Anagram. Let's understand what this problem is asking us to do. We are given two strings, S and T. Our task is to return true if T is an anagram of S. Otherwise, we return false. So, what exactly is an anagram? An anagram is a word or phrase formed by rearranging the letters of a different word or phrase. The key point here is that we must use all the original letters exactly once. For example, the word listen is an anagram of silent because we can rearrange the letters of silent to form listen. Now, let's look at the constraints. The length of both strings S and T can be between 1 and 5 times 10 to the power of 4. Both strings consist of lowercase English letters only. These constraints tell us that our solution needs to handle strings up to 50,000 characters long. Keep this in mind as we develop our approach. Let's look at our first example to understand this problem better. We have S equals anagram and T equals nagram. Our output is true. Why is this true? Let's break it down. Both strings contain exactly the same characters with the same frequencies. The letter A appears 3 times in both strings. The letter N appears 1 time. The letter G appears 1 time. The letter R appears 1 time. And the letter M appears 1 time. Since nagram is formed by rearranging the letters of anagram, they are anagrams of each other. That's why we return true. This example shows us the basic case where two strings are valid anagrams. Now, let's look at example 2, which shows us when strings are not anagrams. We have S equals rat and T equals car. Our output is false. Why is this false? Let's examine the characters in each string. The string rat contains the letters R, A, and T. The string car contains the letters C, A, and R. Notice that the character T is in S, but not in T. Also, the character C is in T but not in S. Since the two strings do not contain the same characters, they cannot be anagrams of each other. That's why we return false. This example shows us an edge case where the strings have different characters entirely. Let's start with the brute force approach to solve this problem. The key idea is to sort both strings.
Think about it this way.
If two strings are anagrams, they must contain the same characters with the same frequencies. When we sort both strings alphabetically, they should become identical. Here are the steps for this approach. First, check if the lengths of S and T are different. If they are different, we can immediately return false because anagrams must have the same length. Second, sort both strings alphabetically. Third, compare the sorted strings. Fourth, if they are equal, return true. Otherwise, return false. This approach is simple and easy to understand. Let's see how we implement this in code. Now, let's look at the implementation of the brute force approach in Python. We start with our class solution and define the function isAnagram. It takes 2 parameters, S and T, both strings, and returns a Boolean. First, we check if the lengths are different. If length of S is not equal to length of T, we immediately return false. This is an optimization because anagrams must have the same length. Next, we sort both strings. We use the sorted function to sort S and store it in sorted_S. We do the same for T and store it in sorted_T. The sorted function in Python converts the string into a list of characters and sorts them alphabetically. Finally, we compare the sorted strings. If they are equal, this returns true. If they are not equal, this returns false. This code is clean and straightforward. It follows our approach exactly. Let's analyze the time and space complexity of our brute force approach. Starting with time complexity, it is big O of n log n. Let me explain why. Sorting a string of length n takes big O of n log n time. This is because most efficient sorting algorithms like merge sort or quick sort have this time complexity. We sort both strings S and T. So we have big O of n log n overall time complexity. Here, n is the length of the strings. Since anagrams must have the same length, Both strings have the same length n. Now, let's look at space complexity. It is big O of n. The sorted function creates new lists to store the sorted characters. We create sorted_s, which has size n, and sorted_t, which also has size n. So overall, we have big O of n space complexity. Again, n is the length of the strings. This space is used to store the sorted versions of our input strings. Now, let's explore the optimal approach to solve this problem. The key idea is to use character frequency counting. Instead of sorting the strings, we can count the frequency of each character in both strings using a hash map, also known as a dictionary in Python. If both strings have the same character frequencies, they are anagrams. Here are the steps for this approach. First, check if the lengths are different. If they are, return false immediately. Second, create a hash map to count character frequencies in S. Third, iterate through T and decrease the count for each character in the hash map. Fourth, if any character in T is not in the map, or if a count goes below 0, return false. This means T has a character that S doesn't have, or T has more of a character than S does. Fifth, if all characters match perfectly, return true. This approach is more efficient than sorting. Let's look at the implementation of the optimal approach in Python. We start with our class solution and define the function is anagram. It takes two parameters, s and t, both strings, and returns a boolean. First, we check if the lengths are different. If length of s is not equal to length of t, we return false immediately. Next, we count character frequencies in s. We create an empty dictionary called count. Then we iterate through each character in s using a for loop. For each character, we use count to get with two arguments, char and 0. This returns the current count if the character exists, or 0 if it doesn't. We then add 1 to this value and store it back in the dictionary. Now, we decrease counts for characters in T. We iterate through each character in T. If the character is not in our count dictionary, we return false. This means T has a character that S doesn't have. Otherwise, we decrease the count for that character by 1. Then we check if the count is less than 0. If it is, we return false. This means T has more of this character than S does. Finally, if we complete both loops without returning false, we return true. This means both strings have the same character frequencies. Let's analyze the time and space complexity of our optimal approach. Starting with time complexity, it is big O of n. This is much better than the brute force approach. We iterate through string s once, which takes big O of n time. Then we iterate through string t once, which also takes big O of n time. Dictionary operations like get, insert, and lookup are big O of 1 on average. This means each operation inside our loops takes constant time. Overall, we have big O of n plus big O of n, which simplifies to big O of n. Here, n is the length of the strings. Now, let's look at space complexity. It is big O of 1, which means constant space. The hash map stores character frequencies. But here's the key insight. Since we only have lowercase English letters, there are at most 26 different characters. The space is bounded by a constant, big O of 26, which simplifies to big O of 1. Even with very large inputs, the hash map never exceeds 26 entries. This is why we say the space complexity is constant, not dependent on the input size. Now, let's understand the connection between the brute force and optimal approaches. The key insight is that both approaches verify that strings have identical character frequencies, but they do it in different ways. The brute force approach uses sorting. It rearranges characters alphabetically and then compares the sorted results. The time complexity is big O of n log n due to sorting overhead. This approach is simple but inefficient for large inputs. The optimal approach uses a hash map. Finally, let's compare both approaches side by side in a table. Looking at the approach row, the brute force method uses sorting, while the optimal method uses a hash map. For time complexity, the brute force is big O of n log n. The optimal approach is big O of n, which is significantly better. For space complexity, the brute force is big O of n because we create sorted lists. The optimal approach is big O of 1, which is constant space. This is because we only store at most 26 characters in the hash map. Finally, looking at what each approach is best for, the brute force is good for a simple solution that's easy to understand. The optimal approach is best for optimal efficiency, especially when dealing with large inputs. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.